Okay, so with that brief introduction, I would like to welcome Julia Jeworrek to the session. And if you can share your slides, Julia, she's going to present on post-processing sub-daily precipitation forecast with analog ensembles in Southwest BC. So please take it away.
Yes, I would like to present some work in progress today on analog ensembles for precipitation forecasts in Southwest BC. This work is being supervised by Greg West and Roland Stahl, and we are all part of the weather forecast research team at the University of British Columbia in Vancouver. Greg is also a meteorologist for BC Hydro, and Compute Canada, or it's called Digital Research Alliance of Canada now, they provided us with research allocations to conduct this work. So BC is located on Canada's west coast, and the climate here has essentially two modes, a cool and wet season and a warm and dry season. And BC also has very complex terrain, which locally enhances precipitation, and that makes this area very attractive for hydroelectricity. However, extreme events can occur on both sides of the spectrum. So for example, in November last year, we had a series of atmospheric river events that caused intense flooding and mudslides, and Vancouver was essentially cut off because all major roads were either damaged or flooded. On the other side of the extremes, there can be dry spells in the warm season, and those can lead to drought and wildfire. So precipitation forecasts are very important, especially for BC Hydro, because they have to plan and manage their reservoir operations accordingly. We try to enhance precipitation forecasts in two parts. First of all, by tuning the numerical weather prediction setup, and secondly, by post-processing the model output. And this talk focuses on a statistical post-processing technique called analog ensembles. The analog technique derives a post-processed weather forecast for a target model forecast by looking for similar model forecasts in the past and using their corresponding observations to compose an ensemble. And because the analog ensemble is directly a result of this relationship between past model forecasts and their observations, they directly correct for the systematic model error. So we basically construct a post-processed ensemble forecast from a raw deterministic model forecast. And the first step in finding analogs is to base this method on a skillful numerical weather prediction model. So for the year 2016, we had evaluated over 100 configurations with systematically varying physics parameterizations. And we identified 3 configurations that performed best across different metrics and precipitation intensities. And these results are already published in the Weather and Forecasting Journal. So now we want to post-process these best WRF model configurations to see how much further we can enhance the precipitation performance. But because analogs or analog ensembles are a data-driven method, we require a longer hindcast data set. So I ran those best setups for an additional almost 5 years. And because each of these 3 configurations comes also with 3 grid spacings, we now have nearly 6 years of a 9-member multi-resolution and multi-model ensemble. And we split up this data set into roughly 5 years for the training and optimization period and 1 year for the verification. And we use observational data from 46 stations across Southwest BC. And the model data is extracted at these station locations. And for 41 meteorological variables, those some of them are available at different levels, and some of them are derived from other variables shown in red here. Next, we have to define how analogs should be identified. So to define in what way we want these past forecasts to be similar to our target forecast, we need predictors. And those predictors can then be put into a similarity metric, which attaches a score to all of the past model forecasts. And the highest ranking ones are used to build an ensemble. And here I'm showing a very popular similarity metric for analog ensemble forecasts. It basically standardizes the difference between the target forecast and the past analog model forecast. And you can also apply a unique weight to each of the predictors. And you can even choose a time window surrounding the target time to be considered in this similarity score. So we started with a very simple investigation of predictor relationships between the observed precipitation and all of the model variables. And we actually looked into various metrics and feature selection techniques. Here I'm just showing one example, the Spearman correlation coefficient and how it varies for different variables by season or by month. And it became quickly evident that predictors vary with season and location, but they actually don't vary too much with the different model configurations. And of course, some of the variables in my list are also related to each other. So including several of such correlated variables would be redundant because they don't add any additional information. So from our complete data set for 41 variables, it's now our goal to identify a subset of variables that are optimal predictors for precipitation at each station and each season. So we looked into different predictor selection techniques, and as a reference here, we use a static predictor combination of precipitation and integrated water vapor. This has been used in other studies before. And another common approach in analog ensemble predictor tuning is a brute force approach, where you basically try out all of the different combinations. But then Alessandrini suggested to use a simplified brute force approach, where you still test all the different combinations, but only one step at a time by adding one variable at a time. And that makes it a little bit computationally more feasible. So we implemented this forward selection approach in different variations. So first of all, you can use all of the variables, and then in this wrapper framework, we would add one variable at a time, run the analog ensemble, and assess the performance until we identify the subset of predictors that provide the best performance. The problem with that, again, is it's still computationally quite expensive and it takes quite long. So we wanted to assess whether we can start this process with fewer variables by only including variables that are more likely to have valuable predictor relationships. So in another trial here, we ranked all of our variables by their distance correlation coefficient with the observed precipitation. And then we start this forward selection with only the top 10 variables. And then finally, we developed a predictor selection score that includes more statistical metrics, and again, only use the top 10 predictor candidates. And to show you what we did with this predictor selection score, it's the result of 3 metrics. There's again this distance correlation coefficient, but also the maximum information coefficient. Both of these metrics account for nonlinear relationships in slightly different ways. And we also account for the variance inflation factor, which detects multicollinearity among variables. So when I build this ranking of my top 10 variables, I test the variance inflation factor. And if one variable is strongly correlated with the pool of previously selected variables, then I skip this variable, move on to the next. And in addition to these 3 forward selection methods, I also wanted to experiment with principal component analysis derived predictors. So this idea is basically assuming that the principal components might be better predictors for general meteorological conditions. And here again, I tested first all of our variables, including precipitation. Then I started the principal component analysis with only the top 10 variables based on either the distance correlation coefficient or the predictor selection score. And then finally, I experimented with a hybrid where precipitation was fixed as our first predictor. Then I ran the principal component analysis on all of the remaining variables, and then I performed a forward selection technique on those principal components to select their individual weights for the similarity score. So I want to assess which of these methods are best, but it is also computationally expensive to test all of these. So I performed a limited predictor and selection sensitivity study with a smaller subset of my data. Here I only tested this for 10 stations and for 1 model configuration, and only for the first 24 hours after spin up. And here I'm showing the resulting 75th percentile threshold weighted CRPSS, that's the continuous ranked probability skill scores. We decided to optimize for this metric because this way we can focus on significant precipitation events. Negative values in this score mean that the method performs worse than the control run. And vibrant or darker colors here show the results of the training period, and lighter or more transparent colors show the result of the testing. And the first very obvious result is that all of my PCA methods, which are shown in the red box plots, they overfit the training data because they perform a lot worse than the testing. And if we now zoom in to the more meaningful scales here, we can see that the purple hybrid method improved the overfitting, but it still performs poorly even for training. And it's really only those forward selection methods that show the performance increase over the control run. And we performed some sensitive or hypothesis testing and could not, and it seems like the difference between those three forward selection methods are actually not significant. Here you can see the pattern of the selected predictors and their weights across the 10 stations. And this is here just shown for the predictor selection score. But if you compare the absolute differences between the resulting predictor weights between those three forward selection methods, we can see that the two methods that use that only use a subset of the variables, they are most similar to each other, which is shown by the shorter orange bar, so smaller differences. And between the two 10 variable methods, the one using the predictor selection score is more similar to the one using all variables, which is shown by the shorter red bars compared to the yellow bars. So in conclusion, we've seen that the forward selection is the best predictor selection technique that we have tested. We also saw that we can effectively reduce the input variables, saving computational cost while not significantly reducing the optimization skill. And the predictor selection score filters better predictor candidates than the distance correlation alone. And just to give you a quick outlook of our further future plans, we are now investigating also the time window consideration in the similarity score to identify better accumulation windows. And we are also looking into different ensemble composition methods. And I actually presented some of the preliminary results on this at the AMS conference in January. So yeah, if you're interested, feel free to reach out to me. I guess I left a few minutes for questions, but yeah, thank you very much for listening.